And welcome to Unit 7, Lesson 3, Derivatives of Inverse Trig Functions. This does correspond to Section 5.6 in your text. There are parts of that section that you aren't going to be able to do because they also talk about how you integrate inverse trig functions, but we're just going to pick out the derivative piece of that. So where does this fit into your overall tool bag of derivative rules? So we first learned that the limit definition obviously can apply theoretically to any function, but it's not efficient. So our basic differentiation rules apply to when we have polynomial form. If we don't have polynomial form, we look for the opportunity of a product or a quotient, and we would apply that formula. If we see that it is a composition, we use chain. Then we have implicit differentiation rules. Related rates was just an application of implicit. Related rates isn't another differentiation tool in your tool bag. And so we also have regular trig derivatives that you have to know. So your sine, your cosine, etc. And now in this lesson, you are going to add your derivatives of your inverse trig functions. So that's kind of where this sits in the overall schema. Before we actually talk about what are the specific inverse trig derivatives, we're going to talk about a pattern of how derivatives exist in general with any inverse that comes your way. So that's going to be the first part of this talk. And then the second part, we will talk about the specific formulas for the inverse sine, the inverse cosine, etc. All right, so here we go. This is, again, this introduction is just about a relationship or a pattern that exists with general functions and their inverses. So let's, for an introductory function, let's take f of x is equal to x to the fifth plus 2x minus 1. The 0.12 is on there. If you need proof, all right, so to prove that this point is on the function for you, I can find f of 1, which is 1 to the fifth, plus 2 times 1 minus 1. So that's 1 plus 2 minus 1, which does give me 2. So hopefully that's proof that to you that that point is indeed on the function. So here are some ways that you could go about this problem. They want you to find, well, what is the point, what is the derivative at the point of 2, 1 on the graph of the inverse? So the idea is you could take y equals x to the fifth plus 2x minus 1. You could switch the x and the y, and you could solve implicitly, or excuse me, you could differentiate implicitly and plug into 1. I want to acknowledge that that is an absolutely valid way of finding this answer. What I'm trying to show you is that if I just have f of x, I'm going to be able to answer this without ever knowing what f inverse of x looks like. So how can I answer this? Let me give you an easier example. All right, so let's look at f of x is equal to x cubed plus 1. What is the inverse of this function? Well, we have y equals x to the third plus 1. We're going to switch the x and the y, and then we're going to solve for y. So the inverse of this function is going to be the cube root of x minus 1. And just for your knowledge, if we want to make a sketch of both on the same axis, okay, that was f. And now if I put in its inverse, we're going to have the cube root of x minus 1. And so this is the graph. And notice that the two graphs do reflect over the line y equals x. Maybe we'll put that in there so that you can see. Right? So they both of the graph and its inverse reflect. So here is the idea. We're going to come back to that graph. Okay, we can differentiate. So to be clear, f of x is equal to x cubed plus 1. The point that lies on x cubed plus 1 is 1, 2. All right, let's look at that. Let's graph the point 1, 2. So that point right there lives on the graph of f. I can determine its specific slope there. So f prime, that delayed weird, f prime of x is equal to 3x squared. And if I want to find f prime of 1, the derivative there is specifically 3. So again, if I want to do the exact slope at that point, it would be a slope of up 3 over 1. All right, I can figure out the derivative of its inverse. The derivative at f prime, oh, let me be consistent here. Hold on, before I differentiate, remember on an inverse that if 1, 2 is on the graph of f, that means 2, 1, I switch the x and y, would be on the inverse. So just to show you that, if I plot 2, 1, notice how that is its corresponding point reflected over the line y equals x on the inverse of f. So f prime inverse. So let me just write it out in English. This is kind of obnoxious symbolic math. So when I want to find the derivative of f inverse, I would get 1/3 x minus 1 to the negative 2/3, technically times 1 by chain rule. And then when I evaluate the derivative of the inverse at 2, remember that would be the proper input, I would get 1/3 times 2 minus 1 to the negative 2/3. Well, that's just 1/3 times 1 to the negative 2/3. 1 to any power is 1, so I get 1/3. So this is the pattern I want you to see, that the derivative at 1 on the graph of f has a specific slope of 3, but it's 1/3 at its corresponding point on its inverse. What is the pattern between those two? They are reciprocals. So the idea, this is what happens on for any inverse. On any inverse, all right, and I wish they would let me write on this app, but they don't. But if you look at the point 1, 2 on the red graph, and you look at the point on the blue graph, those are inverse points on their inverse functions, and their slopes are reciprocals of each other. So let's go back to our introductory problem. And this is how I would do this on, say, an assignment you might have to turn in for NAP. All right, so here we go. This is how, now that I know that they're reciprocals, again, I'm going to be able to answer this question without ever knowing what the inverse function looks like. If I know f of x is equal to x to the 5th plus 2x minus 1, then its derivative is 5x to the 4th plus 2. The point 1, 2 is what lives on f of x. So I'm going to evaluate f prime at 1, and this gives me a specific slope of 7 at the point 1, 2, which is on the graph of f of x. My question is asking me, well, what is the derivative of f prime at 2? That's because on the inverse function of f, the 0.21 exists on that. Therefore, the derivative of the inverse at 2 would be the reciprocal, so the answer to that is 1/7. I hope you enjoyed that little conversation regarding general inverse relationships between derivatives of inverse functions. And to kind of also sum up, we have a nice little rule that if f is differentiable at every point of an interval, and df dx is never zero. So if the derivative of f with respect to zero, as long as it's not zero, because think about that. If you have zero, its reciprocal would be undefined, correct? So that's why they make that specification. Then we say that f has an inverse and the inverse is differentiable at every point on the interval. And I'm going to let you know that if you are taking specific slopes, that the relationship between them, they are reciprocal slopes. So now let's talk about specific rules for the inverse sine. So what do we know about the domain and range of the sine curve? Well, let's think about this. This is f of x. And we know that our domain is going to be all real numbers. And the range is going to be between -1 and 1. What we also know is that in an inverse, the domain and the range change. So if we are talking about the inverse sine of x, the domain is between 1 and 1 inclusive, -1 and 1 inclusive. But remember, the domain of the sine curve doesn't directly translate to the range of the inverse sine, because then it's not a function. So we restrict the range values on the inverse sine to be between -pi/2 and pi/2 inclusive. So how do we derive the derivative rule for the arcsine of x? So right now I'm giving you the y. Ultimately, there's going to be a formula that you will just have to know and memorize for the AP. All right, so here we go. We are trying to figure out what is the derivative of the inverse sine of x. But remember, I only have basic rules I can use, and this is not polynomial form. This is not a product or a quotient. All right. This is not a regular trig derivative, and right now implicit isn't going to help me. I can't differentiate in the state it is in. However, since this is a true statement, whatever I do on the left, I can do on the right. So what I can do is take a sine of each side, because then I'm given the sine of y is equal to x. And now I can use trig derivatives combined with implicit to differentiate this statement. So when I take the derivative of both sides, we will have to do that implicitly. So the derivative of the sine of y is the cosine of y times dy dx, and that's going to equal 1. So this gives us dy dx is equal to 1 over the cosine of y. But this is not a helpful format. It's not helpful because it's in terms of y. I want it in terms of x. So let's think about this. I do have a rule. This one right here. Let me get a different color. All right. I know that the sine of y is equal to x. Well, is there a relationship between sine y and cosine y? There is. It's a Pythagorean identity. Don't we know that the sine squared of y plus the cosine squared of y equals 1? Therefore, the cosine of y is equal to 1 minus the sine squared of y. And when I take a square root, you technically get a positive and negative principal root. But remember, and this is why we went over this, remember that this is the range of the sine, inverse sine. This means that your y values have to be between -pi/2 and pi/2. So if I am taking cosine values that are between -pi/2 and pi/2, that means the fourth quadrant and the first quadrant, which means every value is going to come out as a positive value because cosine is positive in those two quadrants. So we do not have to worry about the negative principal root. So I'm going to use substitution. So dy dx is equal to 1 over the square root of 1 minus sine squared y. So again, instead of the cosine of y, I wrote it as the positive principal root. And now I go back and I know that x is equal to the sine of y. So my inverse derivative of the inverse sine is 1 over the square root of 1 minus x squared. And that's the y. If you look at the formal definition in the textbook, the reason they use u is any function of x. So if your argument is anything but an x, it's going to require chain rule. So how do I do one of these problems? I'll try to keep both of those in the same pane. When I am looking at this problem, that is not an x. So that means chain rule is going to kick in. In this case, my u is x squared, so that means du dx, or if you prefer u prime, is 2x. So how do I differentiate this? Well, this is my rule. To differentiate the inverse sign, all right, y prime would be 1 over the square root of 1 minus u squared times the derivative of du dx, which is 2x, which yields a final answer of 2x over the square root of 1 minus x to the fourth. The rules for cosine are algebra. You're going to see it very analogous to what we did for cosine. So as a reminder, if I want to talk about y equals the cosine of x, the domain is all real numbers, and the range is in between -1 and 1. But if I want to talk about the inverse cosine of x, those switch, where your domain is now -1 to 1 inclusive, but remember that the domain of cosine of x doesn't necessarily translate to the range of the inverse cosine of x, because then it wouldn't be a function. So on cosine, however, we restrict it from 0 to pi. So what is going to be interesting a little bit later in this proof is this means that your outputs of your inverse have to be between 0 and pi, and that will become an important fact when we have to choose the positive or negative principal root. All right, so again, we're going to start out with the y equals inverse cosine of x, and in this format, we can't differentiate it directly, but if I go ahead and take a cosine on both sides, then I'm left with the cosine of y is equal to x. And now when I differentiate both sides, I have the tools of implicit differentiation and trig derivatives that I can be successful in my differentiation process. So I get the opposite of sine of y, dy dx is equal to 1. Therefore, my derivative is equal to 1 over the negative sine of y. Again, this is not a useful formula because it is in terms of y. We want this in terms of x. So we do this little side work where we know that x is equal to the cosine of y. So maybe there is a way for me to find a relationship between the cosine of y and the sine of y, and that again is the Pythagorean identity of sine squared y plus cosine squared y equals 1. This time I want to solve for the sine. And so again, when I find the sine of y, I get the positive and negative principal root of 1 minus cosine squared y. But again, we talked about earlier that your y values are always going to be between 0 and pi. So if you're taking the sine of 0 through the sine of pi, that's in the first and second quadrants when sine, your trig ratio will always be positive. So this is why we ignore the negative principal root, and I'm going to use substitution to put in the negative square root of 1 minus cosine squared y. And since we know that x is equal to the cosine of y, this yields that the derivative, let me put an arrow, the derivative of the inverse cosine is 1 over the opposite square root of 1 minus x squared. And if we are going to expand this to chain rule, we would have a formal definition that the derivative of the inverse cosine of u would be 1 over a negative square root of 1 minus u squared times du dx. So this would be the chain rule definition as it is stated in the beginning of your textbook, or if you probably look online. So the big difference, if we go back to the question, how does the arc cosine of x relate to the arc sine of x? They are basically the same formula, but one has a negative in it, and that is the inverse cosine. So again, if I had to find the derivative of the inverse cosine of 1 over x, I can consider that this is the inverse cosine of x to the negative first. So y prime is going to be 1 over a negative square root of 1 minus x to the negative first squared times the derivative negative x to the negative 2. You're done with your calculus step. So now I just need to clean it up. I have 1 over, well, this negative and this negative cause it to be a positive. This would be an x squared on bottom, and it would be the square root of 1 minus 1 over x squared. And the algebra of this is kind of crummy. I mean, ultimately, this is an answer that doesn't have a negative exponent, but you do have a complex fraction. So I can make this be a common denominator by multiplying by x squared over x squared. So I get y prime is equal to 1 over x squared times the square root of x squared minus 1 all over x squared. And now see if this makes sense. I can think of this as 1 over x squared over 1 times the square root of x squared minus 1 over the square root of x squared. So what happens is an x comes out, and then what happens is this x can cancel out that x, so I end up with a final answer of 1 over x, the square root of x squared minus 1. The derivative rule for arctangent, I think, is the most straightforward of all of them. Again, falling in line to what we've been doing before, we are trying to find a derivative rule for the inverse tangent of x, but I can't differentiate in that form because this is what we're trying to do. So we are going to take a tangent ratio of both sides, which gives me the tangent of y is equal to x. Now I can differentiate both sides by using implicit differentiation and trig derivatives. So this is going to give me the secant squared of y dy dx equals 1. So dy dx is equal to 1 over the secant squared of y. Again, the issue is this is in terms of y, so this is not a useful formula to use. So I ask myself, well, is there a relationship? Because I know that x is equal to the tangent of y. Do we have something that tangent and secants are related? We sure do. We have that 1 plus the tangent squared of y is equal to the secant squared of y by Pythagorean identity. And there's nothing to solve for. I can put this straight in by substitution. So I have 1 over 1 plus the tangent squared of y. And since I know that x is equal to the tangent y, this yields a derivative of 1 over 1 plus x squared. So if we write this in chain rule format, the derivative of the inverse tan is 1 over 1 plus u squared times du dx. Again, this is assuming that u is not just a plain x, that it is some function of x. So let's do the next example. A particle moves along the x-axis so that its position at any time t greater than 0 is given by x of t is equal to the inverse tan of root t. So just putting this in terms of an application problem, it wants the velocity of the particle when t is equal to 16. So this is implying we want a specific slope. So I know my derivative rule for the inverse tangent is 1 over 1 plus root t squared. times the derivative of root t. So if root t is t to the 1/2, that is going to be 1/2 t to the negative 1/2. Now, as a reminder, let's clean this up a little bit. So I have 1 over 1 plus t times 1 over 2 times t to the 1/2. Well, we wanted the specific slope at 16. So let's input that in for t. So I get 1 over 1 plus 16 times 1 over 2 times root 16. And that gives me what? 1/17 times 1/8. And so x prime of 16 would be 1 over 17 times 8, 5, 1 over 1/36. All right, so now we're going to start a discussion about the reciprocal inverse trig functions. So this is a pretty straightforward algebra proof. What makes arcsecant a little bit goofy to understand has to do with that piece when we're choosing to take either the positive or negative principal root. That's, again, you can just memorize the formula, but hopefully this will give you some insight as to why in the heck there is an absolute value in the formula. All right, here we go. We have y is equal to the inverse secant of x, and we are trying to differentiate that. As we've done in previous proofs, we have no tools, but if I take a secant on both sides, now I have the secant of y equals x, and I can differentiate using trig and implicit differentiation. So now when I find the derivative of both sides, the derivative of secant is secant tangent, and implicitly dy dx equals 1. So dy dx is equal to 1 over the secant of y, the tangent of y. Again, this is not a very useful formula because it's in terms of y, but we know that x is equal to the secant of y. So I can go ahead and substitute so far that I have that dy dx is equal to 1 over x, the tangent of y. But I still have the tangent in terms of y. Well, we know that we have the Pythagorean identity that relates the secant and the tangent as 1 plus the tangent squared of y equals the secant squared of y. Let's solve for tangent. So the tangent squared of y is equal to the secant squared of y minus 1, and that means that the tangent of y is equal to plus or minus the secant squared of y minus 1. So this is where this becomes an issue. I want you to look at the secant function. If you look at the secant of x function, all right, we have this from 0 to 2 pi. Okay, so you're pretty much just looking at this piece. Your derivatives are always positive. The derivative of a secant is always positive in between 0 and pi over 2. Why is that important? It's important because the range of the inverse secant is between 0 and pi over 2, where pi over 2 is not included, and pi over 2 to pi. That's the range of the inverse secant. This translates to the first and the second quadrants. So when I differentiated up here, let me do pink. When I differentiated, I don't like pink. When I differentiated the secant of y, friends, that derivative, this statement, secant y, tangent y, always has to be positive. So when I am in quadrant 1, this formula is a non-issue. I would take the positive principal root, and dy dx is equal to 1 over x, the square root of secant squared y minus 1, which gives me the dy dx is equal to 1 over x times the square root of x squared minus 1. That's cool in the first quadrant. What's not cool is if I happen to be in the second quadrant, because that means that would be the negative principal root. But friends, this right here, that tangent of y can't be negative because the secant is always going to be positive in the first and second quadrant. So in order to make up for that, we put an absolute value on the x in our formula. So you guys, you can memorize this. And you do need to, but I want you to understand that the absolute value is necessary to account for situations when the tangent of y is negative, and it can't be because the derivative of the secant between 0 and pi over 2 positive slope. So you can ask me more in office hours if that is still kind of confusing for you, but this is the derivative of the arc secant. Again, it is done in terms of u, and chain rule applies when that statement is anything but an x. So how do we differentiate y is equal to the inverse secant of 5x to the fourth? Well, this is not x, so chain rule applies. So u is 5x to the fourth. So the derivative of u is 20x to the third. So I just pump this into the formula. Y prime is equal to 1 over the absolute value of 5x to the fourth times the square root of 5x to the fourth squared minus 1 times 20x to the third. So we simplify our final answer. So y prime is equal to 20x to the third. Now, sometimes you have to ask yourself, are the absolute values necessary? Well, they're not. No matter what value of x I put in, it's always going to be positive. So writing 5x to the fourth would be equivalent. And this gives me 25x to the eighth minus 1. So then when I simplify, I get a final derivative of y prime is equal to 4 over x, the square root of 25x to the eighth minus 1. So you might be asking yourselves, are you going to keep proving? We haven't proved arc cotangent or arc cosecant of x. You don't have to. Here is how they relate. We differentiated the inverse sine of u to be 1 over the square root of 1 minus u squared du dx. Well, its cosine was the exact same formula. Oops, that should be a u. Except it was negative. Exact same formula, except it's negative. We proved inverse tangent. So on that same pattern, the inverse tangent was 1 over 1 plus u squared du dx. So that means its cotangent, the inverse cotangent of u, is going to be the exact same formula, only it's going to have an opposite sign in the numerator. So on that, we just proved that the inverse secant of u was 1 over the absolute value of u times the square root of u squared minus 1 du dx. So without having to prove it, it's cosecant. The inverse cosecant inverse trig derivative would be a negative 1 over the absolute value of u square root of u squared minus 1 du dx. Sometimes that's how I remember them. Sometimes you can also use your cofunction identities. And these calculator conversion identities, if you have an Inspire, they're not really necessary anymore because you do have these buttons, you have them on your calculator. So I have these included if you have a TI-84 because you will need them. But if you have an Inspire, you'll never need to use those. So for our last example, differentiate the inverse cosine or cotangent, cotangent. And this is how I think of it. I remind myself that the inverse tangent of u, that its derivative is 1 over 1 plus u squared du dx. So that means that the inverse cotangent is that same formula with a negative. All right, so my u is x minus 1 to the 1/2. So du dx is equal to negative 1/2 x hold on, I bonehead error, caught it, hold up. brain working too quickly. So u is equal to x minus 1 to the 1/2. Hopefully we've survived math therapy. So its derivative is 1/2 x minus 1 to the negative 1/2. Let's put this together. So y prime is equal to negative 1 all over 1 plus the square root of x minus 1 squared times 1 over 2 times x minus 1 to the 1/2. When I simplify, this power of 2 and that cancel, which yields negative 1 over 1 plus x minus 1. That should be a positive. Over 1 over 2 times x minus 1 to the 1/2. These cancel. So final answer is 1 over x, 2x times x minus 1 to the 1/2, or if you prefer radical notation, 1 over 2x times the square root of x minus 1. Thank you for listening. This learning opportunity is your recommended assignment for the week. And you will have on Tuesday, April 14th, you will have the Unit 7 Lessons 1 through 3 review. You need to show your work. And I will see you in office hours, or if you have any questions, comment under this post or leave an email.